Awesome, and thanks everyone for staying almost to the very end of day one. It's been a long day, lots of stuff to fill your heads with, and hopefully we're gonna keep filling it up even more. So I'm talking about the open world execution model, which is for seamless, local first, distributed execution. So the main topic today is how you can connect all of the world's users and services in a way that's open, interoperable, and everywhere. So one way of thinking about this is it's like an HTTP or a TCP IP for compute, not just for moving data around. So a little bit about me. I'm Zelenka. You can find me most places on the internet as Xpeed. I'm an independent developer, and I'm also the editor on a variety of specs, including two that we're going to be talking about today, which is UCAN and the Interplanetary Virtual Machine, IPVM. Programming language theory and distributed systems are my jam, which I think will be apparent through this. And the main company that was behind IPVM sadly went under about 4 weeks ago. So luckily, Perot Labs decided to give an initial endowment to keep the work going. They said, this seems important enough. We'd like to keep this alive, and a number of external teams as well. There's actually more, but these are the main ones for different parts in the stack. If you find this interesting and you want to get involved, come see me after. So, motivation. The internet's changed a lot since the 90s, and we now have new techniques and a new environment in which to operate. And so people have been trying to get rid of place-oriented programming for a long time, and maybe we now have the techniques to do this. So what's wrong with places? I'm going to pick on AWS here a little bit. The pink dots are AWS data centers, and they're distributed roughly like so, mostly in North America, Europe, and the Far East side of Asia. And if you're AWS, this makes sense, right? You can put things, have a really good economy of scale and put things where, users actually are, and you can avoid putting data centers in uninhabited zones like these two, Central America and Africa. That's absolutely false. There's lots of people there. They're absolutely online. They're just not as profitable. And if you're AWS, this totally makes sense. Most of your paying customers are in North America, Europe, and Far East of Asia. But it's not so great for the folks that live in these other places. If you want to talk about just sheer population density, this little circle has 50 million people in it, which is how many people there are per data center in North America. In South America, it's about 500 million people. And in Africa, it's 1.5 billion people per data center. And again, this totally makes sense. You don't have even the infrastructure in the Cape Town data center because they have rolling blackouts, crumbling infrastructure, right? They have to do a lot more work to get this working. If we deploy an application today and we want to send a message from, say, the center of Spain to the coast, it's actually going to take a trip more like this. You're going to send a photo to somebody. It's actually going to go through the Paris data center and all the way back, which is fine if it's a photo and it's not that latency sensitive. But this is a little over 7 times the time, energy, and carbon involved. Now, we keep doing better and better with bandwidth, but we're hitting the limits on latency because the speed of light is finite. The pithy way of saying this is that New York isn't getting any closer to Tokyo, and we can't make those lines much straighter now that we have things like Starlink. Ink and Switch proposed this interesting model about 5 years ago called local first, which says, well, now that we have new things like CRDTs and other ways of replicating data, we've now liberated data from any particular location. You don't have to have the data in the database. You can spread this out a lot more, and we can remove latency by default. We can get that down to 0 and gain ourselves several hundred milliseconds in performance overhead. This is a slide from Ericsson from a few years ago showing things that they need very, very low latency things on, right? Things that most of us care about. We saw a talk earlier today about factory automation. That has in the 1 millisecond round trip time requirements. Smart grid for energy, automated vehicles, et cetera, right? So this is a logarithmic scale from 1 millisecond to 100 milliseconds. You can't do 100 millisecond round trip times in most data centers today. You have to move to at least edge computing, and ideally, if you're in a factory, you have to do it all inside the factory itself. And we're generating a ton of data from lots of places. If you have a modern car, like say a Tesla, it's gathering all this geospatial information and actually has to do processing on device, on the car, because it can't push all of that data, terabytes and terabytes of data every day, over consumer Wi-Fi, right? Where you have IoT arrays that are producing data at such a rate that is not physically possible to keep them all in sync into a data center. So what happens? You have these large stores of data, you compute over them, you dump that data, which means that you now have even more data, and this is called data gravity. So we now hit a point where moving data around to compute isn't practical anymore. We actually have to be able to do the opposite as well and move compute to data, ideally in the lightest way possible. And finally, the network isn't anymore a beige box that sits under your desk that you turn off when you walk away from it, and you assume that the servers in the network are otherwise peer-to-peer. We have a very heterogeneous network that may have to, on a single request, go through very different parts of the system that have very different characteristics, very different kinds of uptime, very different latency. And these all have very different APIs. And that's really difficult to reason about when you're building a system. I don't know about you, but I want to be able to just dip down into some underlying substrate of compute, kind of like having a native API where you're doing things on device, but for it to actually route around and be able to do things like send an email as part of that. Distributed systems are hard, right? I think that's a continuing theme in a bunch of the talks in this conference. The famous Lamport line is that a distributed system is one where a failure on somebody else's machine makes your machine unusable. So the local first approach to this is to say, what if I never or only rarely depend on other people's machines? What if I can make most things run, 95% of things run totally locally because I don't depend on a data center anymore, and I only go to the network when I absolutely need to? And finally, the other way of handling the complexity of distributed systems is if you're able to frame your problem as if it's pure data processing, you then end up in something that looks a lot more like making database queries. And you can completely isolate the developer from the possibility of failure. This is more than durability. This is a property called virtual resiliency. So we're talking about compute today. Compute obviously depends on data, and data in a distributed context depends on auth. We will not have time to talk about data, right? This is a 25-ish minute spot. So you're gonna have to just take it as read that the data replicates everywhere. We can do a discussion about that offline if you want to know more about the details. So, capabilities. Normally when I give a talk about this, I start top down, and I go from the high level into the details. For today, I'm going to do the opposite. I'm going to start from one little slice with WebAssembly and work up through one column of the system, and hopefully along the way, also expose you to some things that can be applied to other things. You don't have to buy into the entire IPVM protocol. So WebAssembly, for those not as familiar, is neither web nor assembly. It was originally developed for browsers, and as a more performant virtual machine that would sit alongside JavaScript, and now has been moved so that it runs absolutely everywhere: servers, client devices, IoT, you name it. And a nice thing about Wasm is that by itself, it is a sandboxed, totally pure function. So even if you're writing in C or Rust or Go, it has a deterministic asterisk, except for one edge case in floating points that you can then put a flag on and force that to be consistent. Totally deterministic, consistent execution model, which means from the outside, it is a pure function, if you treat it like a black box. And pure functions are really easy to work with, right? You just only have to deal now with function composition. But sometimes you need to do a little bit more. You need to talk to a database, you need to talk to a file system, send an email. So the Bytecode Alliance, the good folks that are working on WebAssembly, have this component model where they basically let you put little ports on the outside that the host system, so the thing that's actually running the Wasm, attaches to and says, hey, you want a file system? You're going to get a series of bytes, stream of bytes that represents the file system. And what it actually is could be anything, right? It could be an in-memory system, it could be the actual file system, it could be something over the network. It doesn't really matter. Inside the Wasm, it just sees it as a stream of bytes. And all the semantics about what that thing actually is lives on the outside of the system, outside of the module. If anybody's familiar with CQRS, this has a really nice parallel to that, where you've broken things up into discrete stages. You have queries, pure computation, and mutations. It's actually the exact opposite of CQRS, because you're not, the module isn't producing events onto a stream and then you're running the effects associated with that after. You're grabbing things from the outside world and putting them into the module to run. Okay? So for the really nerdy out there, this isn't an effect system, this is a co-effect system. And the nice thing about this is it has a very natural expression for programmers. You pass in as regular arguments, what basically looks like a handle to all of these different things. So here's our database, file system, and email. We use them inside the body of the function, get something out of the database, loop over it, send a bunch of emails, and then at the end we do the pure value portion. But we're doing this in a distributed environment. That's on one machine. And that whole model is called capabilities, and there's also now distributed capabilities. Distributed capabilities mostly come out of work on authorization. So most people, when they hear about that, they think about access control lists, right? As a quick refresher, here's our user, here's a service, and the user wants to make a request to the service. And they get stopped by essentially a bouncer on the way who says, show me your ID, are you on the cool person list? He goes, yep, okay, great, farmer's on the cool person list, we're going to continue on to the service. And on one hand, this is really nice because we have these 3 distinct steps and you can outsource that middle part, right, the auth portion of this. The downside is that the user and the service aren't in control, that bouncer's in control, you always have to put messages through them, so you're adding extra latency. They can go down, taking your entire system down, they can have bugs, or they can be corrupted. So there's actually a very large surface area for things that can go wrong in this model. And you have a single source of truth that lives in a database somewhere. And now, if you want to replicate out your service and replicate your auth, you have a whole other set of distributed systems problems to deal with. Capabilities work slightly differently. So here's our user, here's our service, and unlike being like a bouncer, it's like getting a ticket to go see a movie, right? Or let's say a festival pass even. You go, you pay, you get the pass, and then they don't have to ID you again, you don't pay again, you just take a ticket and you hand it to them on the way in, they tear it, and they say, yep, great, theater 3. And there's nothing in between here. As long as you can talk to each other, you can complete this request. All the information for this is in that ticket directly. Where the movie pass breaks down a little bit is you can make copies of these and hand them out to other people. So, here's our painter friend, and I'm going to take out, maybe I can't go to the movie on Thursday, so I give him the Thursday ticket, and he can talk to the service now completely directly, without my involvement at all. I can go totally offline. This is a much more direct version of this. And just by comparison, so this is a typical OAuth flow. The yellow section there is the auth server. Here's the setup, the grant process, and then actually using the grant. And if we get rid of that one, we can simplify this quite a lot, right? So here's the setup and use of that. So if you remember this from a few slides ago, we can now replace all of those with these tickets. They're cryptographically signed tokens that you pass around. So you can think of it like a JWT++. Now this is a bit of a lie. Simplifying, we'll talk about the actual properties you need later. But one way of thinking about how the system works is that we can put them on different streams for different amounts of effort required. So for pure functions, they're really convenient, right? 1 + 1 is always 2. If I run it, you run it, we run it in 10 years, it will always be 2. So we can just be really sloppy with this and send out jobs as needed and get results back. We can even do a bunch of jobs in parallel and make sure that everybody's getting the same result if we wanted to. Query effects, so reading something in from the outside world, is also very safe because we're not making changes, we're just ingesting information. And we can do the same thing. We can be relatively sloppy with it, and when it comes in, we bake it down from this thing that happened out in the world that I'm getting data from into, I'm gonna assign that this is the thing that I got back, and now we're back in totally pure land again. And if it turns out that I get, partway through my computation and something goes wrong and I need to roll all of this back, you know what, that's totally fine. We can just roll back and retry it or reuse the result that we got last time. The hard one is mutations. So if we need to send an email, you probably don't want that email to be sent 500 times. So you need to find one specific process, get a confirmation from them, they basically get a lock on it, they do the thing, they come back and they attest, yep, I did the thing. Now, if somebody's replaying over this log, they don't have to rerun the thing again. We know, hey, that thing happened, here was the response we got back. Because we're creating these attestations at every step, that means even as we're composing functions, off to the side we're producing what we call receipts. And because they have explicit inputs and outputs, because they look like pure functions, that means that we can reuse them. We have memoization at global scale. So if somebody else needs the same step, then we can just reuse that and they can continue on with their workflow. Some people in the community have started calling this run once and run never again, because we now have this association between the input hash and the cached output. And we think that there will be a power law where there's a few things that are very, very popular to run, and then a long tail of things that only ever get run once. And those really popular ones end up taking a large part of the system. And we never have to run them again. So if you want to do AI moderation, tagging, grab the last time somebody made something with that LLM input, we can just substitute it directly. You can do expensive operations like cryptographic validation, just run it once, get a bunch of attestations for it. 50 people have already checked this thing, it's probably good. Thumbnails and cropping sort of ad hoc. Without having to go through some central system, anybody in the system that can run Wasm can do that cropping for you, which is every machine. So now we can actually talk about the protocol at a high level. Oh. There we go, okay. So we want to make this relatively easy to use, and much of the pain from distributed systems comes from the mismatch between developer expectation of I've written these things and these things will happen, and then it goes out into the world and all kinds of madness can happen. You can have partial failures, machines can go down, they can be corrupt, all of these things, right? And so we need to constrain the way we program down into some model that makes it more orderly in this disordered domain. Code as data is a very, very old idea. It goes back to at least the late 50s, arguably to the 40s. And basically we say we have arguments, but also our WebAssembly is just bytes. It's a file, right? So it's just another kind of argument. And I can take my arguments, my WebAssembly, and any other configuration I need, like only try this for the rest of the day, things like that. I can take their hashes, put them in a Merkle tree, and say, I now have a unique task ID that if I ask for it or you ask for it, and we haven't done any coordination in advance, we're going to get the same hash. And then when I run it, I create a receipt, it points at that task, we get our pure values out, and then any further continuations that we want. So if it comes back and says, I don't have the ability yet to send an email, could you pass me one of those? It can request that as well. So here's what this actually looks like. It's not that scary. We normally do this in CBOR, but this is the JSON representation. We have the hash of the Wasm. We say this is Wasm run, this isn't sending an email, this is Wasm run. We have the add one function and the argument 42. Great. But what if I don't want to wait for sending that out and having it to come all the way back in, pull the value out of the receipt, put it into the next thing? What if I have a long-running process and I just want to say, hey, when that thing's done, continue with this thing, continue with that thing. Or even if somebody else started the process and I can find the hash for it, for the task, I can say, hey, attach this when that finishes too. This is called promise pipelining. And it works basically like how you'd expect promises in JavaScript to work, but in a distributed setting. We just need to know the hash of the task. And what this lets you do is build up, again, in a very natural way, graphs of computation. And it doesn't matter where these run, what matters is that this is the dependency tree. And we can then break this up arbitrarily. So we can tell the scheduler, hey, these two should run on Alice, or the scheduler rather can tell us, hey, these two should run on Alice and these two should run on Bob, because Alice has a petabyte or an exabyte of data that this needs to run over, and we're gonna push the Wasm to them. Or vice versa, hey, this is a really big Docker container, you should send us the photo that you want us to process, right? And any way of breaking these up still has the same meaning, it has the same semantics. So we can break this up any way that we want to, and it still works. Like I said before, this is trying to be almost like an HTTP of compute. HTTP doesn't know anything about your application. We don't need to know anything about the kind of job that you're running. Everybody can run Wasm, but if you have something else, the system should be able to support that too. The protocol doesn't need to get in the way. All you need is some sort of matchmaking process in the middle. So we use a DHT for the totally open version, but you can use any mechanism as long as you can talk to each other about this. And basically, you register a Wasm component in your node, and it says, hey, I can run these kinds of things. And somebody shows up and says, maybe it's I have a GPU, very powerful GPU. You can run GPU jobs on me. And somebody says, I have a CUDA job to run. And they can find each other, and it gets sent to them. Now, the virtual resiliency that we were talking about way, way back at the beginning, the three properties that we actually care about are mutability, idempotence, and determinism. So will this change the outside world? If I run it once or more times, do I get a different result? And is this deterministic? Do I know exactly if I were to run this again, would I get the same result? What this lets us do, then, is we can interleave pure computation and queries as much as we like, as long as mutations come at the very, very end. Everything else we can always roll back, retry, do whatever we need to do, delay, grab previous results. Mutations are the dangerous one. If we were to interleave like this, we can't roll back. So the one constraint you have for the safe version is you only get one mutation. If you have multiple, then you have to put it into basically a force flag. And what this lets us do is if we have some graph of computation, well, this is also, if you think of time from top to bottom, this is also a valid interpretation of that graph, and it's now safe because we can run everything before we run that mutation, before we send the email. So, to wrap up, compute, like data, like networking, should be a ubiquitous commodity. You should depend on having compute around because every device runs Wasm, and you should only go to the network when you absolutely have to. This gains you hundreds of milliseconds in latency, and you don't have these trust problems of maybe they're buggy, or maybe they have been corrupted, or they're down, right? We want a consistent functionality between clients and the ability to find people or find providers who can do those things for us if we can't do it ourselves. And just like TCP/IP, just like HTTP, we shouldn't, there were networking protocols before those. Everybody had their own custom one. Open protocols and nodes are awesome because it frees us from having to do all of this work and all of this thought. So this is the latest plea of attention from the web. It's not semantic markup. It's not easier layout. It's an open platform, and this time we mean it. Thank you.